So last week we finished up on limits and seeing if a limit exists, looking at a graph, looking at it algebraically, and then maybe even making a table and plugging in values, getting really close to x equals a, if that's what the limit we were taking was going to, and plugging it into the function to see if it went to one particular value or not, and looking at the left and the right-hand side of a limit. We've kind of talked about continuity a little bit while we've been going through this, but this next section is talking about being continuous. So in the past, when we've talked about functions being continuous, you might be familiar with polynomial functions. Polynomial functions are always continuous, but all we said was they were pretty much just smooth, and there was no jumps or holes in the graphs. You could tell that it was continuous if you could just draw it without having to lift your pencil up to make the picture. But that's not really mathematically precise. And so we're going to get into it so where we can prove it. So here's the following. And we've actually been kind of doing some of this when we were looking at limits and showing if they exist. So continuity at x equals c. So we say a function f is continuous at x equals c if there are the following three conditions are satisfied. So all three of these conditions have to be satisfied. If you come to one of these and you show that it doesn't work, then you can just show it doesn't work and say because this condition isn't satisfied, then it's not continuous there. So, and you can do these in any order. But one of the conditions is when you plug in x equals c into your function, it's defined. So for instance, let's see, is it right on here? So we had some instances maybe where we had some jump in the graph. Here, I could say this is C. We have one solid circle below, one open circle above. But here I could say that f of C is defined, and maybe this was A, and maybe this is B. So f of C is our y value of A. So this is a case where it's defined, and you can see that it's not continuous. If I had had both open circles on both sides there, instead, and I didn't have a point above these open circles, then this would be a case where f of c was undefined, and we would say that the limit didn't, well, in that case, the limit doesn't exist, but that doesn't mean we saw that limits could exist when it was undefined at a value. But it's not continuous, is what I meant to say. Okay, so see if it's defined. We need to show that the limit exists. So remember when we were showing the limit exists, you had to show that the limit as x approaches your value, in this case c on the left of f of x, has to equal some value L, but the limit as x approaches c on the right of f of x, remember, also had to go to the same value of L in order for that to exist. So left and right have to be the same in order to exist. If they go to the same value, then the limit we would say as x goes to c of f of x is equal to L. And then the last thing that we have to show is that this f of c value that's defined is the same number that we got back when we took the limit as x went to c. And the limit as x approaches c of f of x is equal to f of c. Which in our case, I called that L. Okay, so again, if one of those maybe multiple of those won't hold, but if one of those don't hold, then we say that it's not continuous. So if f is not continuous at x equals c, it is, we say, discontinuous there. Okay, so I had pulled these last week and put them in this OneNote. So I do have my textbook now, which I'm very excited. But since I have them here, I'm just going to use them. So in exercises 1 through 6, find all the values x equals a where the function is discontinuous. Okay, so we're looking at any value x equal a where the function is discontinuous. And we want all those values. Okay, so for each point of the discontinuity, give a f of a if it exists. B, we're going to look at the left-hand side limit of f of x. We're going to look on the right-hand side of the limit of x as x approaches a. D, and we're going to look at the limit as x approaches a, and then identify E, which condition for continuity are not met. Okay, so be sure to note when the limit doesn't exist. So looking at that, I hope you can tell what value of x this does not exist at, or where the limit does not exist. So looking at that, and maybe you can throw it in the chat, or you can, well, throw it in the chat. So looking at that graph, where would the limit not exist? Where is the left-hand side not the same as the right-hand side? Okay, so I was asking you guys to look at the graph and determine which value it looked like it was discontinuous. And then I mentioned that we want to look at where does the limit not look like it approaches the same y value on the left and the right. And so you guys came back with -1. And so let's go through here and let's do part A. So part A says find f of a. So we want to find f of a. In this case, our a value is equal to -1. This is where we're showing where we think it's discontinuous. And so we want to look at f of -1. So looking at f of -1, so this is saying when x equals -1, what is your y value? So looking at that, what y value do you get back, or do you get a y value back? Does it exist? So anywhere on here at x equals -1, do we have a point? And so notice that we do have a point here, right? And so when x is -1, we have a y value that is 2. Okay, so this exists. Now we want to go and look at part B. And part B says we're going to look at the limit as x is coming, in our case, to -1 on the left-hand side of f of x. Okay, so looking at -1 as we come in on the left-hand side. So go find the function, the graph on the left that's closest to it, which is here, and see what y value you're getting closer and closer to as you come in on the left. And you're coming in, getting back +2. But if we look at it as we're coming in on the right-hand side, so looking at -1, going to the picture directly to the right, if we do this, we're getting closer and closer to not including a value of y equals 4. C. D wants to know, does the limit exist? So the limit as x approaches -1, these are not the same values of f of x does not exist. And then part E, identify which condition or conditions for continuity are not met. Be sure to note when the limit doesn't exist. Okay, so we showed that it was defined. F of C was there, f of -1 in our case. Did the limit exist? Well, left and right exist, but they were different, so the limit actually did not exist as you approached it. And so that is the condition that did not hold. Okay, so this needs to hold. And so if our limit doesn't exist, it makes sense that that limit is also not going to give us our f of c value. Doesn't exist equals 2. That doesn't hold either. So also the limit as x approaches c of f of x does not equal f of c. Okay, so we can see where what we were learning before, this is helpful when we were looking at continuity, before we were looking at limits. So looking at this example, this next graph, you should be able to determine where this looks like it's not continuous. And looking at this, I see that I have this open circle here, and I have a point here. And so we have to make some sort of jump in this graph to get to this point. And so this is not continuous. And so in this case, I would say that we're looking at the value where a is equal to 1. In part A, we want to look at find, in this case, f of 1. So when x is 1, what is our y value? Which is 2. We need to look at the limit as we come in on the left, as we're approaching 1. So coming in on the left, as I get closer and closer to x equals 1 on the left, my y value is getting closer and closer to, not including, but still getting closer and closer to the y value of -2. Look at the limit as x approaches 1 on the right. Well, if I come in on the graph on the right, that y value I'm getting closer and closer to is also 2, -2. Since these are the same, then I can say that the limit as x approaches 1 of f of x equals -2. That was part D. But part E, notice that f of 1 is 2, and the limit as x approaches 1 is -2. And so those are not the same values. And so this is the condition that's not holding. So f of 1, I probably should have done it the other way, but it doesn't matter what part is on the left or right. So f of 1 does not equal the limit as x approaches 1 of f of x. And because of this condition, f of x is not continuous at x equals 1. It doesn't mean it's not continuous everywhere else. It looks like it's continuous everywhere else. So therefore, f of x is not continuous at x equals 1. Okay, so looking at the following example, determine where it's not continuous. I'm just going to blow this up so I can have more. So I noticed in this graph, this graph, there's multiple places where it's not continuous. So notice that we have what is called a vertical asymptote here at the y-axis. So basically the graph on the left-hand side of this y-axis, as you're getting closer and closer to x equals 0, that graph is shooting down to negative infinity. And it's never gonna cross or touch this y-axis, but it will get really close to it. Same thing as we're coming in on the right-hand side, this graph is shooting downwards and going to negative infinity and can never cross or touch a vertical asymptote. And so that means that this is discontinuous, or I can see that it's discontinuous at x equals 0. And notice that there's an open circle on the graph here. And so it's also discontinuous at x equals 2. So let's first find f of 0. Well, like I was saying, there's a vertical asymptote at x equals 0. And so again, you can never cross or touch a vertical asymptote. And so this is undefined. There is a vertical asymptote at x equals 0. Same kind of idea if we look at this and we looked at x equals 2. So if we go to 2 and we look at find f of 2, this is a different scenario. We have an open circle here, and I don't see any point that is falling above x equals 2. And so this is an open circle, there's no point, and so it's undefined. So it does not exist because of the open circle. And no point above or below. So PT for me is shorthand for point. D and E, remember, was do not exist. Okay, so that's the first condition. F of C at that value, x equals C, had to exist. So right there, because of this, you could stop. This was just asking you to go through and that would be just practice of looking at limits. So we could see, does the other values exist? So look at the limit as x approaches 0 on the left-hand side of f of x. And so coming in on the left, we're using this piece. It's not going to any one y value. It's shooting downwards. It's going to negative infinity. So even though we said that when it goes to infinity or negative infinity, it doesn't exist, we tend to like to still put which way it's going. So we kind of know more about what's happening with the graph. That's the whole point of limits, is to see what's happening when we get really, really close to this x value. And so looking at the limit as x approaches 0 on the right-hand side, of f of x, that graph is also shooting downwards, so it's going to negative infinity. It doesn't exist. Even though they're going in the same place, going to negative infinity, they don't exist. So limit as x approaches 0 can't exist. So obviously then the limit as x goes to 0 of f of x does not equal f of 0. I know they're both undefined, but they don't equal. To look at the, now going to x equals 2, we showed that it was undefined at x equals 2. We also want to look at looking in the limit as x approaches 2 on the left. Look at the limit as x approaches 2 on the right. Okay, so if I'm looking at 2 and I'm coming in from the left-hand side, the y value I'm getting closer and closer to looks like negative 2. The same thing as I'm coming in on the right-hand side, at getting closer and closer to the x value of x equals 2. My y value I'm getting closer and closer to is negative 2. So since those are the same, we can say the limit exists as x approaches 2. And we can say it equals negative 2. So another stipulation that doesn't hold with the rules of continuity is that this limit here, as x approaches 2 is negative 2, is not the same thing as f of 2, which we said was undefined. So limit as x approaches 2 of f of x does not equal f of 2. Okay, so let's look at some following examples of where a function could be discontinuous or continuous. So we have different types of functions that we're going to look at. So polynomial functions, and the definition looks a little scary, but it's not too bad. So a polynomial function is written mathematically as y is equal to a sub n, that is times x raised to the nth power plus a sub n minus 1 times x raised to the n minus 1 power plus dot, 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 plus a sub 1 times x plus a sub 0. And this is where our a sub n minus 1, our a sub 1, and our a sub 0 are all real numbers and not all 0. The other stipulation they did not write in here, which also has to be the case, is that n has to be a whole number. Okay, so basically that's just saying that the numbers in front of your variables are not imaginary numbers, they're real numbers. So you can't have an I in there. Square root of a negative is imaginary. The other thing that this is saying is that all of our exponents to the variable are going to be positive, and we're not going to have any fractions. And so that's what it means to be a polynomial function. And so for a polynomial function, where is it continuous? We're never going to have a problem with a polynomial function. They're always continuous. They're always smooth and continuous curves. And this is just an example of what a graph might look like. Okay, so other types of functions that we're going to look at are rational functions. And those are functions where you have a polynomial in the numerator divided by a polynomial in the denominator. But we have to be worried about values which set our denominator equals 0. It's undefined when we have values that set our denominator equal to 0. And so when we're looking at rational functions, if we're trying to find where it's discontinuous, you want to set both the numerator, you want to factor both the numerator and denominator. So with these, let's first factor the numerator and denominator. You want to find the values which set the denominator equals 0. And the numerator equals 0. Really, we're really only worried about the denominator equals 0 because those are the values where it's undefined. But knowing where the numerator also equals 0, it can tell us what's happening at that value where it's undefined. There's two different possibilities that can happen when you have a rational function and you see the values that set the denominator equals 0. You're going to either have a hole in the graph at that value. So there's two possibilities here. So at these values, you either have a hole in the graph, and that's if it's both setting these equal to 0, or it's a vertical asymptote. So at these values, you either have a hole or a vertical asymptote. And so usually when I'm talking about asymptotes, and sometimes we're talking about horizontal ones, just to save some time in writing, I'll say VA. Okay, so let me just kind of do a side note there, like I just explained, but write it, because I know some of you, if you just had intermediate algebra at our school, you might not have seen graphs of rational functions. This is where I was saying I think college algebra is really important as a prerequisite for this course, because you've seen these types of graphs and know about these. But so let me just kind of go a little more in detail a little bit. And so at these values, either you have a vertical or whole or vertical asymptote. So again, if it's just the denominator equals 0, so it just sets the denominator equals 0, it's a vertical asymptote. And if it sets both, equal to 0, then it was a whole. Is a hole in the graph. Okay, so another thing that's kind of important is that you know how to factor. I'm not gonna, we'll kind of explain going through the factoring process as we go through problems, but if you don't remember how to factor, that's something that you wanna go and brush up on. And there's a lot of great videos on factoring that you can find, worksheets, etc. Okay, so another thing that we have to worry about, so that was our rational functions, a polynomial divided by a polynomial. The other type we have to think about are root functions. And really, and we can do this a little bit, set this a little differently. We can say the nth root of ax plus b. And we have to say where n is even. So basically, we're looking at where our domain, we're looking for our domain, where does the values not exist? And so if you have a radical, and it's an even powered radical, so like the square root, the fourth root, the sixth root, that root we're taking is even, then the number underneath that radical has to be positive or 0. If it's a negative number, then we get back a complex number and it's undefined there. And we wouldn't have that piece of the graph. And so what you're going to do is to figure out where it's continuous, and it's going to be continuous anywhere where it's defined. You're going to set what's underneath the radical, which we call the radicand, ax plus b in this case. We want to set this greater than or equal to 0. And this is what our graph looks like. So I'm gonna pause a little bit because this is kind of part of it's typed up, so you guys have time to finish writing that up before I move on to the next one. Okay, so now let me move this up. And so the other types of functions that we look at are exponential functions. Exponential functions, that's where you have some real number as your base, and then we're raising that to some variable, some power. Exponential functions, we say those are continuous everywhere. And depending on your value of your base, depends on the shape of this graph. So in this case, they're graphing where your a value is actually greater than 1. if you were graphing a function where your base was between 0 and 1, the graph kind of looks like this, or it does look like this. General shape, depending on the base, it could be growing faster or slower, but as x is going to positive infinity, we're getting closer and closer to the x-axis, not hitting it, but getting closer and closer to it. So we actually have horizontal asymptotes there. The other stipulation that we have to say on this is that a cannot equal 1. It's not an exponential function if your base was 1, because basically 1 to any power is 1. And so we'd always get back 1 no matter what we plugged in. If we had y equals 1 to the x, anything we plugged in here, we would get back 1. So basically that's just a horizontal line through y equals 1 and not exponential. So a couple cases have to hold in order for your base in order for it to be an exponential function. If your base was negative, it wouldn't be exponential because it would bounce back and forth between positive and negative numbers depending on did you plug in a negative or a positive value for x as your exponent. I'm sorry, it actually not has to do with negative or positive. It has to do with if you plugged in an even or odd number, depends on if that y value you get back is positive or negative, right? So for instance, let me just do it because I slaughtered what I was trying to say. If I had this and I had that x equal 1, right? When I plug this in, I get negative 2 to the first power, which is negative 2. I get a negative number. And if I plug in 2 here, I get negative 2 quantity squared. So negative 2 times negative 2 is 4. And so I'm going to be bouncing back and forth between negative and positive numbers, depending on if x was odd or even. So that's why a has to be bigger than 0 to be exponential. And then I believe this is the last type of function we're going to be looking at are logarithms. So basically logarithms are just exponentials, just kind of written in a funky way. They're basically exponents. And so you can recall definition of logs basically. If we have y equals log base a of x, this can be written differently. So this is what value can I raise a to? What is the exponent to get back x? So this is if and only if a raised to the y power is equal to x. And again, certain stipulations have to hold. And so we have to have our base has to be greater than 0. Our base can't be 1. And the values we get back are always going to be positive. Okay, so basically when we're looking at these, what we're trying to do is set this greater than 0. So I actually might have something like y is equal to log base a of some function rather than f of x, or just x there. Then in this case, what we want to do to make sure that it's continuous is set f of x greater than 0. Okay, so we're not going to get into as many logs as you would in calculus for the STEM majors, but logs are really helpful and useful in taking something that's really, really complicated and being able to rewrite it as something simpler, as sums and differences, so that we can, in the future, we haven't talked about it yet, but take the derivative or integral of something. Okay, so let's look at the following examples. And I'm not going to do all of them. This is just pulled from the text, and I So looking at, let's say, number 7. So find all values of x equals a where the function is discontinuous for each value of x. Give the limit of the function as x approaches a. Be sure to note when the limit does not exist. Okay, so looking at f of x in number 7, we have a rational function. I have a polynomial in my numerator, 5 plus x, and I have a polynomial in my denominator, x times x minus 2. If needed, to find where it's discontinuous, you would factor the numerator and denominator. But looking at this, it already seems factored. So I want to really determine when is my denominator equal to 0. Those are the values where it's undefined. So I'm looking at when is, let me just write it, so find when x times x minus 2 equals 0. These are values. Where f of x are undefined. Okay, so there's 2 values. When you have factors, something factored on one side set equal to 0, we can use a rule that then one of these has to be 0, and so we can set each factor equal to 0. So we're looking at when is x equal to 0? Well, that already, we don't have to solve for x there. And we're looking at when is x minus 2 equal to 0. Okay, so you should also know how to solve linear equations. And so solving linear equations, you get variables to one side, numbers without variables on the other side. And so you want to add 2 to both sides. And so we get x equals 2. Okay, so technically x cannot be 0 and x cannot be 2. It's undefined. So it might ask us what the domain is, and let's just kind of review. So domain are all values of x that you can plug into your function where you're going to get back a real number. Well, you're not going to get back a real number if it's undefined there. And so when I'm looking for the domain, I'm pretty much looking for my trouble spots, depending on what type of function I have. And so if I go back up to my list above, I have trouble spots where I have a rational function where it sets my denominator equals 0. And so those one thing I'm looking for when I'm looking for the domain. If I have something with a square root, I'm looking to see, is it an even power? If there's no power or number shown here, we say it's 2. And if it is, then our domain has to be where that value underneath the radicand has to be greater than or equal to 0. This is going to give us our domain. We said it was continuous for exponential, so domain's going to be all real numbers. And then for logarithmic functions, I'm going to have trouble spots. If I take a log of a negative number or a log of 0, I can't have that. It's undefined. And so I would look at when is that log of whatever I'm taking, could be just x, set that greater than 0 and solve. Okay, so our domain, and a lot of times we like to write things which are called interval notation. And so writing things in interval notation, I feel like I'm doing a lot of review of algebra right now. One way I think that the easiest way to see it is, let's look at the number line. Here, if I looked at the number line and I shaded everything where x was defined. So if I put where it's not defined at 0, and it's not defined at 2. So a couple of things I can do here. I can put an open circle there to express to myself that it's undefined. And I know any other number I can plug into this equation and I would get a real number back. any number you chose other than 0 and 2, you plug it back in here, a real number comes back, so it's part of the domain. And so interval notation for our domain, look at, we're coming in from negative infinity. So we're hitting all the numbers that are negative until we get to 0. So negative infinity, comma, and 0. So we have to be careful with the notation that we put on the end of this interval notation. If it's not included, which it's not, we denote that with a parentheses. Plus, so plus, we're going to do union, which is a U, upside down U, well, I guess not upside down. And we're starting, but not including, getting really, really close to 0 on the right, like 0.00001, but not including. So we put a parentheses 0, and then we're including all the numbers until we get to, but not including 2. Union 2 to infinity. So these are all the x values, they're not points. This means x values. So the range of x values here. So a lot of times if I know it's undefined, sometimes I'll do the parentheses like this and not the open circle, just because it then kind of shows exactly what I have in here. But it's up to you. Either notation is correct. Okay, so we just found all values where x equals a is undefined for number 7. And now we want to look at the limit. As x approaches a. This is where some of those limit rules can be helpful. And so let's again recall that, so limit rules. If f of x is a polynomial, then we know that if f of x is a polynomial, then we know that the limit as x approaches c of f of x is equal to f of c. So also recall that, what was I going to say? Oh yeah. So that was one rule that we're going to use here. Another rule is if we have a limit as x approaches c of a rational function, so maybe f of x over q of x. Again, f of x and q of x are polynomials. Then this was the same thing as a limit as x approaches c of our numerator f of x all over the limit as x approaches c of our denominator q of x. So we're looking at the limit as x is approaching, let's look at one of them, first 0. Of 5 plus x all over x times x minus 2. So this is the same thing as a limit as x approaches 0 of this 5 plus x all over the limit as x goes to 0 of x times x minus 2. So go in here, wherever you see an x, we're going to replace it with 0. And so we have 5 plus 0 all over 0 all times 0 minus 2. So we get 5 plus 0 is 5. 0 times negative 2 is 0. This is not in the form of 0 over 0. We saw last week if we get the form 0 over 0, that was an indeterminate form, and that's where we had to manipulate it and get it so it wasn't that. If you get a number over 0, that's where it's undefined. And so we'll say that this is undefined. Does not exist. So undefined. So the limit doesn't exist. Let me just see what it was saying. So for each value of x, give the limit of a function as x approaches a. Be sure to note when the limit doesn't exist. So how could we tell what's going on here? Can we tell if it's blowing up to positive infinity or negative infinity? Another way to look, let's see. Well, think about if we looked at the limit as x is approaching 0 on the left. When I plug in numbers in here, let's just think about it. If I plug in numbers in here, I just want to know if I have a positive or a negative number back, technically. If I plug in a number close to 0 on the left, 5 plus a little negative number is still going to be positive. And a negative number times a negative number, because a negative 0.01, something like that, minus 2, that's negative, is also negative times negative is positive. And so positive over positive equals positive. And so this goes to positive infinity. Choose upward on the left. And then looking at it on the right-hand side, I can kind of do the same sort of reasoning. I can tell myself, okay, when I'm plugging in values, x approaching 0 on the right-hand side, I'm plugging in a positive number close to 0. Well, 5 plus a positive number close to 0 is also positive. And then a positive number times, well, 0.01 minus 2, I'm getting close to 0. So 0 minus 2 is negative, times a positive is negative. So this is equal to a negative number, negative infinity. So this is actually shooting downwards as x gets closer and closer to x equals 0 on the right. Okay, one more value what we said x could not be, which was 2. And same sort of reasoning when we go back in here. So when I look at the limit as x approaches 2 of our function 5 plus x, all over x times x minus 2. So technically I'm using these limit laws. I'm not going to write it. So I can just go in here and I can plug in 2 wherever I see an x. So we have 5 plus 2 all over 2 all times 2 minus 2. So if we simplify our numerator and denominator, well, 5 plus 2 is 7, all over 2 times 0. So 7 over 0 is undefined. And then we can start seeing if it's shooting upwards or downwards as x approaches 2 on the left. So let me just think about it. If it's coming to 2 on the left, it's like 1.9 minus 2 is negative. So negative times positive, this is going to be going down to negative infinity. So this probably turns around somewhere, I don't know where, but it comes back down and something like that. And then as x approaches 2 on the right, so plugging in values like 2.01. So 2.01 there, that's positive in the numerator, all over 2.01, which is positive. And 2.01 minus 2 is also positive. So positive over positive is positive. And so this would be shooting upwards over here. Just give you a general idea of what that function would look like. And let me just show you real quick, and then we'll take a break. So our numerator, I'm going to put parentheses so it knows that I'm plugging that in. I have x plus 5, all divided by parentheses, put it in there, x all times x minus 2. So as x goes to 0 on the right, that was shooting upwards. As x goes to 0 on the left, it's shooting downwards. Later on in this course, we'll be able to find this value. This is called a local maximum point. We'll be able to have tools with calculus to find this number, but not now. But I knew that, again, as x was approaching 0 on the right, it was shooting downwards. And then this is x equals 2. So x equals 2 on the left-hand side. Again, I said it was going to negative infinity, but on the right-hand side, it was shooting upwards. So we had a general kind of sketch by knowing what those limits of those couple values were. Okay, so this is probably a great spot to take a little bit of a break. Okay, so we're looking at, again, continuity and just coming back from break. And now let's look at problem number 10 in this one. And so we want to find all values x equals a where the function is discontinuous. So we have a rational function, so we want to find when our values, what value set our denominator equals 0. I noticed that our function f of x equals x squared minus 25. I noticed that numerator factors. I have 2 terms in the numerator, and notice that they're a difference of squares. And so recall, if you had something in the form of a 1 term squared minus another term squared, this factored as whatever you would have to square to get the first term minus whatever you squared to get the second term, and whatever you squared to get the first term a plus whatever you squared to get the second term b. Doesn't matter order, it could have been a plus b all times a minus b. And so there is something I can square to get x squared. And so in this case, this is the same thing as x. And what I can square to get 25 is 5. So I can factor this as x minus 5 all times x plus 5. All over my denominator, it doesn't factor of x plus 5. So the domain of f of x, we have to exclude any values which set the denominator equal 0. Okay, so we cannot have x plus 5 cannot equal 0. And so if I solve for x there, I know that x cannot be negative 5. So any other number I choose for x, I can plug it into this function and I'd get back a real number. The only number that would give me a problem is when x is equal to negative 5. So we could say a couple different ways. In an interval notation, we would look at all the numbers from negative infinity until we get really, really close to negative 5 on the left. And we have a parentheses union, and then negative parentheses, negative 5, comma, infinity. So like I mentioned a little bit earlier, it depends on what value. If it sets both the numerator and denominator equal to 0, then that would be a hole on the graph. And if it just set the denominator equals 0, then it is a vertical asymptote on the graph. So looking at this, if I look at when is x minus 5 equal to 0, that's when x is 5. And then when is x plus 5 equal to 0, that's when x is negative 5. So x equals negative 5, both sets the numerator and denominator equals 0. So that tells me I have a hole on the graph. So since x equals negative 5, sets both the numerator and denominator equal to 0, then there is an open hole on the graph. Or open, yeah. At the point, we can actually figure out what that y value is going to be when x is 5, what that open circle, when it's getting closer and closer to on the left and the right. And how we can do that is, notice our function f of x here, that in factored form was x minus 5 all times x plus 5, all divided by our denominator, which was x plus 5. So we have common factors in the numerator and denominator. Maybe you see it more if you have that parentheses there. And so even though x cannot be negative 5, if we simplified this and we canceled out like factors, we have f of x can be reduced to just x minus 5. Again, x cannot be 5. I'm sorry, negative 5. But if we look at f of x equals just x minus 5, and we go in there and we plug in negative 5, even though it's undefined there, into what we're left with, we have negative 5 minus 5. So negative 5 minus 5 gives us back negative 10. So it's an open circle at the point negative 5, negative 10. Okay, so find all values of x where x is discontinuous We said x cannot be -5, so that's where it's going to be discontinuous. But we also want to look at the limit. And so remember, and this is where if we looked at the limit of our original function there, so the limit x is approaching -5 of x squared minus 5, or x squared minus 25, all over x plus 5. And we go in and plug in -5 wherever we saw an x and reduce it using the rules, limit rules. So we have -5 quantity squared minus 25, and then -5 plus 5. So doing that, we get 25 minus 25 in the numerator, which is 0, all over -5 plus 5 in the denominator, which is 0. So this is an indeterminate. So that's where we had to go back and see how we were going to manipulate this so that something fell out other than 0 over 0. And so that's where one of the things that is helpful is by factoring both the numerator and denominator if possible, which we did factor the denominator. I'm sorry, we factored the numerator earlier. And so this is equal to the numerator factored as x minus 5, x plus 5, all over our denominator of x plus 5. So now if we cancel like factors, this would be equivalent of looking at the limit as x approaches -5 of just what's left, which is this x minus 5. And so plugging in -5 here, wherever we see an x, we get -5 minus 5, which gives us -10. Okay, so limit as we approach x equals -5 on the left, and the right equals -10. But if you look at the graph, there's actually an open circle on that graph. And we're getting closer and closer to x equals -10. The y value is getting closer and closer to -10, but not including it. And since, though, the limit, well, there's two things that hold for discontinuity. So it's not continuous at x equals 5, -5. So not continuous at x equals -5 because the following conditions do not hold. Following conditions for continuity do not hold. Well, first of all, f of c, or whatever value we thought it was not continuous on, had to be defined and give you back a value. And we saw that at x equals -5, it was not defined. So one of them that doesn't hold is f of -5 is not defined. And the other case, the limit does exist and they're not the same. So the limit as x approaches -5 of f of x is not the same thing as f of -5. Okay, so let's kind of look at a different type of an example. Actually, I don't know if you guys realize, but the absolute values are really piecewise functions. So basically, you have a certain equation for values of x if they're less than this, and you have another equation for values of x which are greater than that. We looked at piecewise functions before. Maybe let's just do that again. Let me pull one of these. So maybe the absolute value of 5 minus x all over x minus 5. Let me just graph that, or give myself more room. Okay, so we're given again, in this case, it was r of x instead of f of x. So r of x is defined to be the absolute value of 5 minus x all over x minus 5. So we want to rewrite this without the absolute values. So let's rewrite the absolute value of 5 minus x without absolute values. Okay, so before we do that, just let's look at the absolute value of x. Well, two things can happen. You can either plug in positive numbers in here. So this is equal to. If you plug in a positive number in there, it's just equal to x. And this is if x is greater than or equal to 0, right? So if I plug in 0, the absolute value is still the same thing I just plugged in 0. If I plug in 1, the absolute value of 1 just gives me back what I plugged into the absolute value, which is just 1. But remember, if you plug in negative numbers and take the absolute value, you always get back a positive number. And so if I take the absolute value of negative 1, then to get back positive 1, I have to take the negative of the negative, right? So really, this is equal to negative x if x is less than 0. Some of you might have see this actually in reverse order where you're, coming up on your x values, but it's just saying the same thing. So this is saying if you choose any number less than 0, so negative 5 falls in the category of less than 0. To find out what the result, your output would be, you'd plug it into this piece of the equation. So negative of negative 5 is positive 5, which we know absolute value of a negative number again is positive. And so this is basically the piecewise function for the absolute value of x. And so we want to do the same exact kind of thing for 5 minus x. And so we want to find out what value inside this absolute value, when is that going to give us back positive numbers. So when is 5 minus x is greater than 0? Even greater than or equal to 0 is fine. So solving inequalities, you have to be careful when dividing by a negative. I'm going to, or divide by a negative, you have to flip your inequality sign. I'm just going to add x to both sides of my equation to isolate it. So I have 5 is greater than or equal to x. I tend to like my variable on the left-hand side. It makes more sense to me. And this is the same thing as saying x is less than or equal to 5. So any number smaller than or equal to 5, then we would look at just this value. Okay. So we're looking at 5 minus x if x is less than or equal to 5. So that means numbers that are smaller than that, the value I would get back would be the negative of that result. So if I look at the negative of 5 minus x, we're going to use that result if x is bigger than 5. So just kind of think about it, just showing you that's true, but with a result. Go away. So if I chose some number that falls in one of these categories, so let's say 6. 6 is bigger than 5, so that would tell me I'm using this equation. So if I looked at 6, and I plug that in wherever I saw an X. I wish my colors were working. I'm stuck on black. Oh, maybe not. So I plug in 6 there. This is saying that I would get back the result of negative. And now I'm stuck on red. 5 minus 6. So 5 minus 6 is negative 1. And negative of negative 1 is positive 1. So if you went back in here and you did absolute value of 5 minus 6, simplify. This is an absolute value of negative 1, which we know that gives us an output of 1. Okay, so we need to see where this is equal to 0, where it's undefined. And that's values which set the denominator equals 0. So this is at x equals 5. And now we want to look at the limit as x is approaching the value where it's undefined, where we're going to have a discontinuity. Of the absolute value of 5 minus x all over x minus 5. If we go back in here and we plug in 0 wherever we see an x, we get the absolute value of 5 minus, I'm sorry, not 0. If we go back in here and plug in 5 wherever we see an x, we get the absolute value of 5 minus 5 all over 5 minus 5, which we get the 0 over 0, which we said was an indeterminate. But if we go back and we use this fact right here, then we can break this up. So technically, if I can say that the limit as x approaches 5 of the absolute value of 5 minus x all over x minus 5, well, it depends on which side I'm coming in on. If I'm coming in on the left-hand side, that means that my numbers are less than 5. Then I would be using this equation. So the limit as x approaches 5 on the left, x is less than 5, we use this equation. So we're going to use 5 minus x all over x minus 5. If we plug in 5 in wherever we see an x, you get 5 minus 5, which is 0, all over 5 minus 5, which is 0, which is an indeterminate. but that's okay, because I can see I can factor that pretty easily. Notice 5 minus x and x minus 5, they're almost identical. They're just off by opposite signs in front of each one. So this is a positive 5, or this is a negative 5. This is negative x, where this is a positive x. So we can go in and we can manipulate this where we factor out a negative 1. So we can say, well, hey, then this is the same thing as the limit as x approaches 5 on the left. Let's pull a negative 1, and I'm just not changing colors. Pull out a negative 1 from 5 minus x. Well, that would make this negative 5 plus x all over x minus 5. Well, these are exact same thing. And so we can actually technically simplify, and we would get back negative 1. Actually, yeah. Because this would technically be saying the limit as x approaches negative, or x approaches 5 from the left, of negative 1 is equal to negative 1. So I want to do the exact same thing I was just talking about, but I want to do it for this piece. So let's look at values of x where x is coming in on the right-hand side to 5. If that's the case, this is telling me the numbers I'm plugging in are bigger than 5. If they're bigger than 5, it tells me I need to use this piece for the numerator of that absolute value. And so this would be the same thing as negative, parentheses, 5 minus x, all over this x minus 5. If we go back in and we plug in 5 for x, again, we get 5 minus 5 is 0 times the negative out front is 0. We get 0 over 0. But if you distribute that negative, we kind of manipulated it a little bit, we get the same thing we have on the denominator. Right, so we get negative 5 plus x. By commutative property is the same thing as our denominator, x minus 5. Those simplify by canceling each other out. This is the same thing then as saying the limit as x approaches 5 on the right of 1. We're just left with 1 there, everything else canceled. This is equal to 1. So only if our limits are the same does the limit exist. So not the same. So the limit as x approaches 5 of f of x does not exist. Because of this property, the graph is discontinuous. At x equals 5. Or because that property doesn't hold. Sorry, it's kind of trying to get everything in there for you. Okay, so we'll go over some more examples on continuity on Wednesday. We'll look at piecewise functions more, where we're not rewriting an absolute value as a piecewise function, where you're just given a piecewise function, trying to find values where we can make it continuous, and then a couple of applications, and then maybe jumping into 3.3, which is average rate of change and instantaneous rate of change.